Today we'll be looking at discrete random variables and their application to probability distribution tables. Now the first skill that we need to do is to be able to calculate the probable chance of consecutive events happening. So in example 1 here it says a jar contains 4 white balls and 6 black balls. So there's two things here. Either something will happen and it's drawn out as the colour white, or we'd draw out the colour black. And because we can see that there's 4 white and 6 black, we know that there's a total of 10 within the bag, or within the jar rather. So the first thing that we want to do in kind of recognising what we have and what we know is we start with the probability of white being drawn. Well, that's going to be 4 out of 10. There's 10 total and 4 of them are white. The probability of black being drawn is equal to the remaining 60% chance, or 6 over 10. Now the question asks, what is the probability, let's just change that. What is the probability that a white ball will be drawn exactly once? And the context that it gives for us is if 3 balls are drawn at random from the jar with replacement. And that's a really big key critical word there that it says with replacement. It means that we don't need to recalculate the chance every time. It means that every time they draw a ball, they're going to put it back, and so there's always a 40% chance of white and a 60% chance of black. Now in order to figure out what the probability is of a white ball being drawn exactly once, we need to start modelling the sample space or the situation at hand. We can do this with a tree diagram, or we could have a look at what we know the sample space to be. Now, just like flipping a coin, there's 2 options, either white or black, and this time it's asking us to draw 3 instances of these options. So we know that we could go 4 whites, 4 blacks. We know that we could go 2 whites, 2 blacks, 2 whites, 2 blacks, and white, black, white, black, white, black, white, black. Now if there's a binary outcome, so either white or black, this is a really easy way to list the sample space. Otherwise you could draw the tree diagram and work it out, but with enough practice you'll realise the questions are always asking things like flipping a coin or yes or no response. Any kind of binary response, we're going to be able to do this. So the question now becomes, what happens, or what are the options in which there is exactly 1 white ball? So we can have a look at one of the first options here. We've got white, 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 so there x would equal 3. White, white, black, x would equal 2. White, black, white, x would also equal 2. And the first situation we see is white, black, black. So if we imagine what the probable chance is there, we know that we've got 0.4 times 0.6 times 0.6. We also know, if we go a little bit further down, that we could go black, white, black, just down here. Now the chance there would be 0.6 times 0.4 times 0.6. And the last possible outcome just underneath that, black, black, white, would be 0.6 times 0.6 times 0.4. So there are 3 instances in which x equals 1, and we know that we could add up all these instances in order to find our outcome. Now if this were a non-calc, we could think of these as the fractions. So we've got, if I highlight this here, 6 over 10 times 6 over 10 is 36 over 100, and 36 times 4 is the same as saying 30 times 4 plus 6 times 4, so we get 144. Now you notice that all of these are the same. So, doing 6 times 4 times 6, or 6 times 6 times 4, or 4 times 6 times 6, that doesn't matter. So we know that we could think of this as simply saying 3 times 144 over 1,000. So 3 times 100 is 300, 3 times 40 is 120, so we're at 420, and 3 times 4 is 12. So we end up with 432 out of 1,000. It's really important that we bring context to our answer, and we can see in the question here that it gave us the situation where x equals 1, so assuming that x is the number of white balls that have been drawn. So to put this back in context, we'd say the probability of x equals 1 exactly is equal to 0.432. Now you might be wondering, why do we bother with saying something like x equals 1, or why don't we just write the probability of one white ball? And it's because this information can be presented as a probability distribution table. If we scroll down a little bit, we'll see that most probability distributions look like the below form. In the top bracket here, we're referring to the number of favourable outcomes. So if we defined x as being the number of white balls drawn, we could say that there's 1, there's 2, there's 3, or there's 4 drawn. We also know that there could be 0 drawn. And so we'd need to account for every option. So here, this is the number of favourable outcomes. Now below it, where we see PR of x, here we're talking about the chance of each outcome. So the chance of getting one white ball, if this was representing drawing white balls out of a jar, would be A. The chance of getting 2 would be B, 3 would be C, etc. Something that we might notice is that if we're saying the chance of getting x equals 3 or 4, so we might model this as saying the probability that x would be greater than or equal to 4 is actually equal to C plus D, because just below it we can see that these are the two chances, and we simply have to add them up. Finally, you might notice that you regularly see this throughout the textbooks and whatnot. This symbol of a capital sigma means the sum of the probability of x for all favourable outcomes x must be equal to 1. Now what that means in this case, or what we might say that implies in this case, is that A plus B plus C plus D equals 1. If we add up the bottom row, it must all equal 1. Now we can apply this knowledge to the question above. It says, consider the table shown. Does this meet the conditions to be a probability distribution? Now for part A, it's pretty simple, but it's a good idea to get used to how we should structure an answer like this. The first part of my answer, I might be thinking, well, what are the conditions for a discrete probability distribution? So we'd want to state something like, for a discrete probability distribution, I'll just shorthand that, the sum of P of x for x must equal 1. Now, since 0.2 plus 0.3 plus 0.1 plus 0.4 equals 1, this does satisfy the necessary conditions. Now, if you think about the structure of this answer, I started with what I needed to state for a discrete probability distribution, the sum of P of x equals 1. I showed that this indeed satisfies that equation by doing since 0.2 plus 0.3 plus 0.1 plus 0.4 equals 1. And then I gave a concludatory statement, thus this does satisfy the necessary conditions. Now part B is also a relatively simple question. It says use the table to find the probability that x is less than or equal to 2. So if I look at the table there and I see, okay, x needs to be less than or equal to 2. So all I need to do is add up everything here. So we might say that the probability that x is less than or equal to 2 is equal to 0.2 plus 0.3 plus 0.1, which is equal to 0.6. Now, as a side note here, we could have thought, well, what is it not? If x is less than or equal to 2, then it's not 3. And so we could have done 1 minus the probability of 3. A little identity here is if we said, and I'll just do this as a side note, in this instance, 1 minus the probability of 3, so 1 minus 0.4, is also 0.26. So we might call it is equal to the probability that x is less than or equal to 2. Now to be fair here, I might have to adjust what's inside here as 1 minus the probability that x equal 3. Just excuse the squishy writing there. So let's apply what we know to example 3. It says let x be the number of heads showing when a fair coin is tossed 3 times. So I know the thing that I have is that x is the number of heads shown, and I know that this is a fair coin that's being tossed 3 times. The question asks me to find the probability distribution of x and show that all probabilities sum to 1. Well, the first thing I'm going to start with is my sample space. So my sample space, again, this is a binary outcome, heads or tails, and there's 3 coins being tossed. So I could do a tree diagram, or I could start with the pattern that I know, heads, 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 tails, 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 tails. So there's 4 heads, 4 tails. Now I'll count by 2s, heads, heads, tails, tails, heads, heads, tails, tails. Now I'll count by 1s, heads, tails, heads, tails, heads, tails, heads, tails. Now because this is a fair coin, there's a 50% chance for heads and a 50% chance for tails. And it actually means that each combination here has the same likely outcome, as everything has a 50% chance. So for my probability distribution table, let's start with, before I start calculating anything, I guess the scaffold for it. I'm going to have x, and I'm going to have the probability of x. I know that if I'm tossing a coin 3 times, there's a chance that I could have 0 heads, 1 head, 2, or exactly 3. Now the question becomes, what does it look like to have 0 heads? Well, the only option there would be tails, tails, tails. So we see that here. Whoops, let's get a highlighter out. This is the only option there, and that's a 1 in 8 chance. There are 8 probable, equally likely options here, and one of them is 0 heads. So we can call this 1/8. Now, how many options are there with 1 head or exactly 1 head? Again, if we had a look at this, we could find that there's an option here. Whoops. Here. We can see there's an option here and an option there. So there's a 3 out of 8 chance. Likewise here, when I'm looking for 2, we could say that there's 2 heads here, there's 2 heads there, there's 2 heads there. So that's a 3 out of 8 chance. And we can see the final thing being that there is only one situation in which we have 3 heads, and that's a 1 out of 8 chance. Now the second part of this question, so the first part certainly said find the probability distribution. We found that. So if I wanted to break up this question into, A part 1 and A part 2, I've done the part 1, but for part 2 it says show that all the probabilities sum to 1. So it would be a shame to have done all this work but not paid attention to the question where it had a second component to it. Show that all probabilities sum to 1. All I need to do in this instance is add up everything I have. The sum of p of x is equal to 1/8 plus 3/8 plus 3/8 plus 1/8, which is equal to 1 as required. So part B now asks us to find the probability that one or more heads show. So for part B, I'm really after the probability that x is greater than or equal to 1. So one or more heads show. I can look at that, and if I'm highlighting here, I'm thinking that's all of this there. So it's everything but 0. So we might rewrite this as that's equal to 1 minus the probability that x equals 0, which is 1 minus 1/8, which is equal to 7/8. Now part C is asking us find the probability that more than one head shows. So this is slightly different. Here we're not including where x equals 1. And I can see that 3/8 plus 1/8, or rather the probability that x equals 2 plus the probability that x equals 3, is just going to be 4/8. And we know that the answer is a half. So the probability that x is greater than 1 is 4/8, or a half. Looking at example 4, it says the random variable x represents the number of chocolate chips in a certain brand of biscuit and is known to have the following probability distribution. So if we break down the question into what do we need x to be, or what do we need to know, we're saying that x represents the number of chocolate chips. It's known to have the following distribution table, so the information that I'm given to answer this question is this entire table. Excellent. Part A is relatively straightforward. It says find the probability that x is greater than or equal to 4. Well, all I really need to do here is think, well, greater than or equal to 4. Okay, so what I'm after, and we might do this in black, is everything that's here. So all that I'm required to do is add up everything that's inside those squares. Okay, well, the probability that x is greater than or equal to 4 is equal to 0.4 plus 0.3 plus 0.02 plus 0.02, and so we end up with 0.74. Part B draws on our knowledge of conditional probability, because we're after the probability that x is greater than or equal to 4, given that x is greater than 2. So the first thing I might do here is start with my formula. I'd say the probability of A given B, in this case being greater than 4, given that x is greater than 2, we know to be the probability of both, so that would be x being greater than or equal to 4, intersection probability x is greater than 2, so one and the other, divided by the probability that x is greater than 2. Now how can something be greater than or equal to 4 and also greater than 2? Well, we can model this on a number line. Suppose we had a straight line here. We said here's 1, 2, 3, 4, 5. The first concept, being greater than or equal to 4, would include 4 and go to the right. The second line would be greater than 2. We're talking about 2 onwards. And we can see that the overlap here, what we're after when we're asking the question both A and B, when we're asking this question, is what's the overlap? And the overlap in this case is just greater than or equal to 4. What is both bigger than 2 and also bigger than or equal to 4? Everything that's bigger than or equal to 4. So we know here that the formula becomes the probability that x is greater than or equal to 4 divided by the probability that x is greater than 2. And remember that we got that from the work that we did above. So we know that we got that from analysing what it means to be both greater than or equal to 4 and greater than 2. Well, we know what the probability of x being greater than or equal to 4 is. We had that above as 0.74. Greater than 2 is everything but 2. So if I look at my table here, we're saying we want everything that isn't this 0.01 or this x equals 2. So we know it's 0.99. So the probability that x would be greater than or equal to 4, given x is greater than 2, is equal to, well, we know it's 0.74 from the question before, and if I do 1 minus 0.01, I'll get 0.99. If I was giving my answer in a non-calc, we can evaluate this to be 74 over 99, and those numbers are relatively prime, they don't simplify. Finally, the question for part C says find the probability that x is less than 5 or greater than 2. Now again, when we look at part C, we'd be thinking to ourselves, this is the probability that x is less than 5 and the probability that x is greater than 2. If we model that on a number line again to help us visualize it, 1, 2, 3, 4, 5, 6, 7 ongoing. Less than 5, well, that very first thing here would look like this. Greater than 2, well, greater than 2 in a different colour would look like this. And so what is in between? Well, the only in between is 3 and 4. So the probability that x is less than 5 and greater than 2 is just the probability of 3 plus 4. So it's 0.25 plus 0.4. So again, putting it back into context of the question, remember our goal is to find x is less than 5 given that x is greater than 2. Well, the probability that x is less than 5 given x is greater than 2 is equal to 0.65, so that's both of them together, divided by the probability that x is greater than 2, divided by the b, the second instance. And we know that that's 0.99. Again, we can simplify this to 65 over 99. Those numbers are relatively prime too. Finally for today, we just want to have a look at a bit of a summary for what we've been doing. We know that for any discrete probability function p of x, the following two conditions must hold. Each value of p of x belongs to the interval 0 to 1. Now that is, 0 is less than or equal to p of x, which is less than or equal to 1 for all x. Well, that makes sense. We can't have a chance that's over 100% or below 0%. So if we're looking at a table that claims to be a probability distribution, we need to, I think previously I showed you need to add them all up and show they equal 1, but they also need to be numbers that sit between 0 to 1. The second condition, the sum of all values of p of x must be 1. Well, yes, here's that very complicated series notation, which we know just means that we can add the bottom row and it should equal 1. Finally, it says to determine the probability that x takes a value in the interval from a to b, including the values a and b, add the values of p of x from x equals a to x equals b. Well, this just means that adding relevant p of x's corresponds to the top row. So previously, we might have found the probability that x was equal to 3 or x was equal to 4. Well, we just have to add up the relevant p of x's. So here, we might just say add the relevant probabilities to find less than or equal to's, greater than or equal to's, less than or equal to's, greater than's, less than's, etc.